In this video, we're going to use the AVR RTC, specifically the periodic interrupt timer, both to wake from sleep and with the event system, where we'll actually stay asleep. The video will give you an overview, but just remember to always check the API reference for the most up-to-date version of the use cases. I'm going to be looking at using the periodic interrupt timer to wake from sleep, and also using the PLIB with the event system. So we'll first add an RTC and the sleep control to the project. Set our clock to 1 kHz. That's mainly actually for the second part when we refactor and use the PLIB out as an event. Enable the PLIB, don't enable the RTC. Sleep control, adding and setting to power down, global interrupt, and then selecting a pin. And this is the code that we will write. So I happen to be using an AVR 128DB48, but you can just as easily use any other AVR supported in MCC Melody, and the principles will be pretty much the same. So adding our RTC, and under system we can add sleep control. We actually want to disable the RTC, but set a clock to 1 kHz. You can enable the PLIB and set a divisor of 1024 to get 1 second. Disable our overflow interrupt and enable a periodic interrupt, which gives us this hint in the interrupt manager about enabling global interrupts. Onto sleep control, we can enable sleep. To check which sleep mode we can use, we'll consult the data sheet. We go to sleep control and scroll down to find this table. You can see that the RTC supports modes all the way down to power down, but with an asterisk there that this is only the PLIB functionality. However, since we are using the PLIB, we can support power down mode. Now, when we wake up, we want to toggle a LED. So we go to our kit window, find our schematics of whichever board we are using. We see that there's a LED on PB3, and that this happens to be a debug IO. So open grid brew, PB3, and this LED. Okay, that should be our configuration. We now go to projects, source, main. Set PLIB ISR callback. We can write a name for this function, whatever we'd like to call it. And all we do here is toggle our LED. Now, in the main loop, we want to sleep the CPU. Note that as soon as we use the sleep CPU, the AVR sleep is included automatically. Program complete, coming into the data visualizer. We want DGI. Going to display a raw, which will plot both debug IO. We can set a couple of cursors. Pause. And you can see we have a 1 second toggle. So part 2 is using the PLIB with the event system. So we have the RTC, we will add the event system. There's the configuration using the outB. We'll look at why that's the case, and then note that we disable all the interrupts and remove the registration of an interrupt and the callback. Resources, drivers, event system, now as we configure, you can see the different PIT channels here. Go to channel 0 and we can see the different event outs. So going to the data sheet, multiplexing considerations, you can see the event system listed here. Event out B is PB2. Now consulting our schematic, we can see that on PB2 we happen to have a debug IO. So that's quite useful for us. And note that it's the different one from the LED. Of course, we could just use any event output and jumper the pins, but this is simpler. Event out B, connect it, and I need to just actually disable the periodic interrupt. And in fact, we should be able to disable global interrupts. Going back to main, we can remove the registration of this callback and the callback itself. So checking in on our pins, after doing that configuration in the event system, we now have an event out on PB2. And if we still want to toggle our LED, well, first of all, let's have a look in the data visualizer. So if we want to toggle our LED, we need to tie these two pins together, the LED and the PB2. Which happen to be right next to each other. So here we tie the pins together, but the application is still working as expected, toggling every 1 second. The LED is active low, so we should really start high so that it's off by default after the initialization. So we're going to generate and program and see what happens here. Okay, so after programming, we still have the same behavior. Our application is actually without any code running. The microcontroller is staying asleep. We are toggling our LED. It's double the speed of what we had before. And if we wanted exactly the same behavior, we'd go back to the event system and instead of 1024, we'll set the event of 2048, and it'll be double that, should be a second. So we generate. Let's program. And there we are. We are back to exactly our original behavior without any code running.